We have previously packaged up the generalized coordinates and conjugate momenta associated with a Hamiltonian system into vectors q and p, and now we will take this process one step further and package both of these into a single state vector z. The time derivative of z is given by Hamilton's equations, and you'll recall that the time derivative of q is equal to the partial of the Hamiltonian with respect to the conjugate momenta. And similarly, the time derivative of the conjugate momenta is given by negative the partial of the Hamiltonian with respect to the generalized coordinates. And that means that we can write this as one big linear system, where we have those two sets of partial derivatives of the Hamiltonian multiplied by this matrix that we will call J. And J has a very specific structure, where the diagonal blocks are n by n matrices of all zeros, and the off-diagonal blocks are positive and negative n by n identity matrices. So we can get the system into this ultra-compact form where we have the time derivative of z is equal to j times the gradient over the state vector z of the Hamiltonian. For a system of n coordinates, j is a 2n by 2n skew symmetric matrix. It is called a symplectic matrix, and it has the following properties. J multiplied by itself, which is sometimes written as j squared, is equal to negative the identity matrix. J commutes with its own transpose, and j multiplied by its transpose is the identity matrix. The determinant of j is strictly positive 1, and as a skew symmetric matrix, the transpose of j is the negative of j and also the inverse of j. Any matrix P is symplectic if the transpose of P times J times P gives you back J. So for any matrix P that satisfies this relationship, P will be symplectic. And J itself will satisfy this relationship, which you can verify using the properties we just listed off. Quadratic Hamiltonians are particularly well suited to this particular representation, because if our Hamiltonian is quadratic in the coordinates and momenta, then we can write the Hamiltonian as 1/2 z transpose mz, where m is some matrix of weights. For this type of representation, the time derivative of our state can be written as j times this m matrix times the state z, giving us a fully linear system whose solution we can write down by inspection as z at time t is equal to the matrix exponential of j times m times t times the initial conditions z0. And we can show that this exponential is itself also symplectic. And the simplest way of doing this is just by plugging it back into this relationship and showing that j pops out. So now let's apply this formalism to canonical transformations. As before, z is going to represent the state associated with our original generalized coordinates and associated conjugate momenta. And we're going to define a new state vector y that is equal to the transformed coordinates, the things we've been calling capital Q, and the transformed conjugate momenta, capital P's, all packaged together into their individual vectors. We will define the coordinate transformation as y written in terms of the original state vector z, and the inverse transformation as z written in terms of the transformed vector y. The new Hamiltonian associated with the system, the thing that we've been calling k, can therefore be generated as the original Hamiltonian written in terms of the inverse transformation of z as a function of y, which generates k, which is a function of y as a function of z, and finally k as a function of y. Hamilton's equations themselves also transform, and so we get the time derivative of y is equal to the time derivative of y represented as a function of the original coordinate z, which can be written as the partial of y with respect to z times the time derivative of z, which is given by our original statement of Hamilton's equations in symplectic form, the symplectic matrix J times the partial of H with respect to Z. And so Y dot is the partial of Y with respect to Z times J times the partial of H with respect to Z. Now we are going to define this partial of Y with respect to Z, this Jacobian, as our matrix M. So in this instance, M is the 2n by 2n Jacobian associated with the transformation of our original coordinates to our new transformed coordinates. And therefore, the time derivative of our new transformed system is this Jacobian M times the symplectic matrix J times the original partial of the original Hamiltonian with respect to the original state vector. From this, we can write the partial of H with respect to Z is the same as the partial with respect to Z of the transformed Hamiltonian written in terms of the coordinate transformation, K of Y of Z. And foiling this out, we get the partial of K with respect to Y times the partial of Y with respect to Z, which we've already defined as this Jacobian M. So the partial of H with respect to Z is the same as the partial of K with respect to Y times M. Due to the nature of this system, this is also equivalent to M transpose dk dy. There's a lot of ways to prove this. The probably most straightforward one is to just write out the component form of this and to verify that everything matches up. We put this back into here and write the final form of our differential equation. The time derivative of our transformed coordinates y is equal to mj m transpose dk dy. Remember, what we're looking for is a Hamiltonian structure, in which case we have just j times the partial of the Hamiltonian with respect to our coordinates. If we want this whole matrix, M, J, M transpose, to be equivalent to J, then M must be itself symplectic. If the Jacobian of the transformation is symplectic, if the determinant of it is equal to 1 and it obeys the symplectic structure properties, then our transformation is canonical, which means that it produces a system that exactly obeys Hamilton's equations. A symplectic Jacobian associated with a coordinate transformation defines a canonical transformation. If M is not symplectic, then you get this system, which does not directly obey Hamilton's equations, but obeys a modified set of equations given by this linear algebraic system. So if M is non-symplectic, your new coordinates don't directly obey Hamilton's equations, but you can still find differential equations for those new coordinates. In general, symplectic transformations are area-preserving coordinate changes that preserve Hamiltonian structure. This is something that we're going to return to when we talk about numerical integration of Hamiltonian systems. However, for now, what we're going to use this for is to take the final step from the Delaunay elements and write differential equations for the perturbation of Keplerian elements. We start with our Delaunay elements, and you will recall the coordinates, the Q vector for this element set was M, lowercase omega, and capital omega. And then the P vector, our conjugate momenta, were given by these alpha values, which were the square root of mu a, the square root of mu a times 1 minus e squared, and the square root of mu a times 1 minus e squared, the whole thing times the cosine of the inclination. We package these into our state vector z. The Hamiltonian is equal to negative mu squared over 2 alpha 1 squared minus any perturbing potential u1. And because this is a fully canonical coordinate set, we can write z dot is equal to symplectic matrix J times the gradient in z of H. Our new state will be the Keplerian elements, A, E, I, M, omega, capital omega, which means that our transformed Hamiltonian will be the energy term from the original Hamiltonian, now written in terms of the semi-major axis, because that's one of our new coordinates, minus the transformation of the perturbing potential, U1, written in terms of z as a function of y. And at this point, the only thing that we have to do to get our new differential equations in y is to evaluate the Jacobian of the transformation from z to y, and then just crunch out the linear algebra, do that matrix multiplication, M, J, M transpose. And that's torturous to do by hand, so at this point, we turn to a computer. This Jupyter notebook recreates the exact derivation process that we've taken to get to the point where we're at now. So we start with the definition of our orbital radius vector in terms of the spherical coordinates r, lambda, and phi, where lambda is the azimuth and phi is the zenith angle. We differentiate it to find the velocity, define the Lagrangian with its perturbation, and then from there go on to define the Hamiltonian and perform the canonical transformation to get to the Hamilton-Jacobi equations and verify that all of the things that we've said are true and that we get our canonical Delaunay element sets. And that brings us to the derivation of Lagrange's planetary equations. We define our original state Z1 as the matrix of all of our betas, which are the mean anomaly, the argument of periapsis, and the longitude of the ascending node, along with their conjugate momenta. And we define our Y transformed matrix as the Keplerian orbital elements. We similarly write both of these matrices in terms of the coordinates and their transformations. The reason why we need to do both of these definitions is because we are going to be doing various substitutions between the two. But in order to generate our Jacobian, we need this form. We need everything to be in terms of the coordinates as written in terms of the alphas and the betas of the system. We generate the Jacobian. That's the Jacobian of Y with respect to Z. And it has this form. Unsurprisingly, it is very, very block diagonal because the betas are elements of our transformed set. All of the betas are in here, the mean anomaly, the argument of periapsis, and the longitude of the ascending node, but the alphas are all functional transformations. And so in this alpha block, we have non-trivial expressions. Here we just have identity and it's 0 everywhere. And so we can see just by inspection that P is not symplectic. And so this is not a canonical transformation. Even though it has the right block diagonal and off diagonal pieces to it, it's clearly not skew symmetric. But that's okay. We know that we can still define a transform set of differential equations. They're just not going to be exactly Hamilton's equations. Our transformed Hamiltonian K is the energy term minus the perturbation term. It looks as follows. And the gradient of K is going to be the differential of K with respect to all of the components of our Y matrix written in terms of the Keplerian elements. And that looks like this. We generate a symplectic matrix J, and finally, we generate our differential equations as P, J, P transpose times the gradient of K, substituting in for all of the various remaining conjugate momenta, the alphas, in terms of their Keplerian element representations. And here we go. These are Lagrange's planetary equations. These are the differential equations for the Keplerian orbital elements in the presence of a perturbing potential U1. We can transcribe these into a slightly neater form, and here they are. So we've finally gotten to where we wanted to go. Remember, we started out by saying that in the case of conservative perturbing forces, we should be able to get an equivalent representation to Gauss's equations in terms of the perturbing potential. Those equations are Lagrange's planetary equations. Here we have the time derivatives of each of our orbital elements as a function of a perturbing potential, which itself can be written in terms of the Keplerian orbital elements. The utility here is exactly the same as the utility we found in Gauss's equations. Just by inspecting the nature of our perturbing potential, we can instantly say which orbital elements will be affected. If our perturbing potential is independent of the mean anomaly, we expect no variation in the semi-major axis of the orbit. If our perturbing potential is independent of the mean anomaly and the argument of periapsis, we expect no variation in the eccentricity, and so on and so forth. Just as with Gauss's equations, there are many, many alternate forms. And once again, I'm reproducing here the two forms found in Batten's book and Volato's book. They are effectively the same as the equations on the previous slide, modulo a few different algebraic simplifications. And also note that in Batten's text, lambda is defined as n, the mean motion, times the time of periapse passage. And these equations are written in terms of both the semi-major axis and the semi-minor axis b, which we know to be a times the square root of 1 minus e squared for closed orbits. You may have noticed that throughout all of this discussion, we have really focused on closed orbits. And this makes sense because this kind of perturbation analysis is really only meaningful for things that are periodic or quasi-periodic. If you have a fully open orbit, then you don't expect the same kinds of forces to be consistently working on it. You can have a spacecraft on an open orbit that is under constant thrust, but then this kind of variational description of it is not appropriate because you are heavily modifying the orbit constantly. What we're interested in is an analysis of small perturbations that have a small but consistent effect over many orbital periods. So we will typically only apply these in cases where we are dealing with closed orbits that are undergoing some kind of constant or periodic forcing. These equations can be directly numerically integrated, or they can be averaged to get a sense of what is going to be happening to the orbital elements on average over the course of many orbits. And the final very important thing to note, our Jacobian associated with our coordinate transformation is itself completely independent of the mean anomaly. The rates of change per orbit of all of the orbital elements to first order can be found by replacing the Hamiltonian with the averaged Hamiltonian over one orbit before taking any partials. And this is consistent with what we've said before about the utility of the Hamilton-Jacobi form of these equations. We can either average our results after we've derived the time derivatives of the various elements, or we can average the perturbing potential before taking any partial derivatives. We now have completed our toolbox for dealing with orbital perturbations. What we need to do next is to actually define some functional forms of various perturbing forces and various perturbing potentials in order to apply these tools.